Swayam Prabha. Digital India. Educated India.
Welcome. So we are in module 5, where basically we are discussing finite element method for Timoshenko beam. So in the last class, basically we have derived the consistent interpolation based stiffness matrix. Now that's one way of deriving it. So or one way of considering or finding out the element stiffness for the Timoshenko beam. So the main problem that we have noticed here is this, that the Timoshenko beam is basically for thick beam or where the shear deformation is not negligible. But this theory should work in case of a thin beam also. So the basic assumption is that dw dx or the derivative of the displacement interpolation should be equals to the theta interpolation in case of thin beam. So to avoid that, we did consistent interpolation, which is different order of interpolation for displacement as well as different order of interpolation for the rotation or the slope. So in this lecture, what I planned is to show another method, which is reduced integration, even though this is required some amount of knowledge of numerical integration, but I will try to explain it analytically. So where by using the reduced integration we can alleviate some amount of locking, or in some cases completely. So the basic idea I will explain here, and then we will derive the stiffness matrix using this method. Now the interesting thing is that the same order of interpolation we can use, that is, if I try to use a linear interpolation for displacement and linear interpolation for slope, that is allowable here, but with certain modifications. So we will see that. So before we start, I just want to briefly recap what we have done, and then I will just write the stiffness matrix that we have derived. So let's see what we have done for Timoshenko beam. So now here so basically what we have done, so in a Timoshenko beam we found out the governing equation. So that is ddx of kappa s, that is shear correction factor, which is coming from the equilibrium shear is parabolic, as we have discussed earlier, and then dw dx plus theta. So theta is my slope. So now that is ksga ddx of dw dx plus theta, and then we'll have force, that is minus q0 or q, it can be function of x also, and then the second equation is ddx of ei d theta dx minus, so we have just modified it, so that is equals to dw dx into your theta plus theta, so that is equals to 0. So this equation with a boundary condition, that is the shear boundary condition, that is KSGA into dw dx plus theta has to be given at x equals to 0 or x equals to L, or displacement W has to be given at x equals to 0 or x equals to L, and then another boundary condition we need, that is EI d theta dx has to be given at x equals to 0 and x equals to L, and or theta has to be given at x equals to 0 and x equals to L. So this is the governing equation that we are actually trying to solve in a weak form. Then by doing the weak form that we have explained in the earlier class, we discretized it or the discrete form of it with the shape functions phi and psi. We derive this kind of equation, which I can write it in a more detailed manner, that is 1 to m k11 ij wj plus summation of j equals to 1 to n. So m and n are order of interpolation for displacement and slope. So that is k12ij theta j minus f of I equals to 0. Here I runs from 1 to m. Now another equation I will get, that is j equals to 1 to m k21 ij wj plus summation of j equals to 1 to n k22 ij theta j minus, this is f1, this is f2, I, that is equals to 0. Here I runs from 1 to n. So where m and n are interpolation order for the displacement and slope respectively. Now this equation finally leads to this stiffness matrix, that is Ke for Timoshenko beam, which has some block matrices. So that is K11, K12, K21 and K22. So this is my stiffness matrix. Now while doing this stiffness matrix, we observe that if I use a linear interpolation function, so if I use something like this, that is W is approximated as 1 minus x by L W1 plus x by L W2, and theta is 1 minus x by L theta 1 and x by L theta 2. So that is, I am considering an element where this is my displacement nodes where I am doing interpolation for the displacement, and this is also my rotation node where I am doing for the interpolation for the slope. So this is similar to what we did for Euler-Bernoulli beam. Now here, since this is not a derivative continuity is not required, because this is theta itself is a primary variable here, so we can use Lagrangian element. So now while doing this, this will lead to actually dw dx dw dx constant, so that is w2 minus w1 by L. So while theta is still linear, so this will create a problem, because in case of a thin beam, actually theta has to be dw by dx. So then theta finally has to be the constant. So now if theta is constant, then bending strain energy for Timoshenko beam, that is ub, is integral ei by 2 integral 0 to L d theta dx whole square. So theta, if it has to be constant, then this theta d x will be 0. So this is defined as shear locking. So now this to alleviate this, we did consistent interpolation. Consistent interpolation. That consistent interpolation means that dw dx, the order of polynomial for dw dx and theta are same. So has to be same. So if this is true, then this problem can be alleviated. To do that, what we did a little different element that we have usually used till now. So we used a 3-noded kind of beam element, but my rotation interpolation in these nodes only. So if I now number the node in this way, that is 1, 2 and 3. So in third node only you have W3, that is displacement, while node 2 you will have only the node 1 and 2 only you will have theta and this W as variable. So so to do that, what we did is basically theta we interpolated with a simple this polynomial, that is linear polynomial, not linear Lagrange polynomial. So but for in case of W, what we did a quadratic polynomial. So W1 phi 1 plus W2 phi 2 and W3 phi 3. Now the phi 1 is all we know, that is 1 minus x by L into 1 minus 2x by L, and phi 2 is actually minus x by L and into 1 minus 2x by L, and phi 3 will be 4x by L into 1 minus x by L. So this is how we did, and then we found out the stiffness matrix. The stiffness matrix, what we have found out is of this form, that is kappa is GA into this equation, that is 7 by L, then this is minus 8 by 3L, then minus 1 by 3L, then 16 by 3L. So then this is minus 8. This is nothing but the quadratic bar stiffness matrix, first 3 by 3 term. So now this is 7 by 3L, and then you will have a rectangular matrix that we have derived in the last class. So minus 5 by 6, minus 1 by 6, minus 4 by 6, and minus sorry, this is plus and this is minus 4 by 6, and this is actually 1 by 6, and this is 5 by 6, and then you will have the bending contribution, that is your alpha by L plus L by 3 minus alpha by L and plus L by 3. So which is composed of bar stiffness kind of matrix and mass matrix. So that also we have seen. So here that is alpha by L and plus L by 3. So this is a symmetric matrix again. So now this equation this is the stiffness matrix. So, in doing so, that stiffness matrix Ke will also have the variables which are aligned now in different way than Euler-Bernoulli beam. So, this is W1, W3 and W2 and theta 1 and theta 2. This must be equals to the UDL or any triangular. So, that means the body force term. So, that is F1, F1, F3 and F2, and then this is 0, 0. So, then again we will have the boundary terms, that is Q1. So, this is Q. So, let me for the third node, let me derive it at Q hat. So, now this is my Q3. So, why I am saying Q3, just to consistent with the Euler-Bernoulli beam. So, now if you remember Euler-Bernoulli beam, that is this is my Euler-Bernoulli beam. So, W1, this is my theta 1. So, W2, that is my theta 2, and then we'll have the shear force like this. This is Q1, this is Q3, and then this is my Q4, sorry, Q2, and this is my Q4. So, this is how we did for Euler-Bernoulli. To be consistent, I just separated out 3, and there is reason why I am doing that. So, we'll understand it shortly. So, Q2 and Q4. So, this is my equation. Now, if you look carefully, that this point actually is only this third node essentially is actually having only displacement variable. So, this displacement variable we can eliminate by considering the third equation in the the second equation we can consider, and then we can substitute W3 this value W3 value in terms of W1 and W2, and then we can reduce this stiffness matrix by eliminating the variable W3, because I am just eliminating W3 in terms of other two variables, that is W1, W2 and theta 1 and theta 2. So, just an elimination procedure. If I follow this elimination procedure, then my final matrix equation looks like, I think this I have not done in the last class. So, this final elimination will look like this, that is KSGA. So, you can just do it by hand itself. So, that is 1 by L minus 1 by L, 1 by L, and this will look like minus half plus half plus half, and this is actually L by 4 plus alpha by L, then minus or L by 4 minus alpha by L, and then L by 4 minus alpha by L. So, here again I think alpha is here, the same alpha here. So, alpha is EI by KS GA. Okay. So, this is just taken common from this thing, because these terms contains bending term contains. So, EI by KSGA is my this thing. So, KSGA multiplied by alpha, KSGA multiplied by alpha is actually EI. So, now this is my stiffness matrix. Now, I arrange it. So, W1, W2, the theta 1 and theta 2. So, this looks like a very simple thing, but only force vector will now change. The force vector will have F1 plus half of F3 hat. So, I will define F3 hat. So, F2 plus again half of F3 hat, and then minus 1 by 8 F3 L and plus 1 by 8 F3 hat L. Now, other terms will be very similar to the Euler-Bernoulli beam, that is Q1 and then Q2 and then Q3 and Q4. I think this is Q3, Q1 and Q3, Q2 and Q4. Okay, so now here essentially if 3 hat is F3 plus Q hat, that is the displacement component coming from here. So this term will come here. So now this is just a similar stiffness matrix that we observed in the similar kind of stiffness matrix that we observed in the Euler-Bernoulli beam, but this contains the all Timoshenko theory of the beam. Now so this is one way of doing this thing. Another way of doing this is, if I have now the stiffness matrix, that is or the interpolation, if I want to use the same interpolation, that is same order of interpolation for W1 or the W and theta. So this if I use, then what was our main problem? The main problem is that our bending energy becomes 0, because at the thin beam limit, or when it goes to thin beam, then d theta dx has to be 0, because the theta becomes constant. Now this is a numerical stuff that we can alleviate that. So this is not a coming from the theory itself. So this is a numerical procedure. So, but it is backed up by the theory. So now what happens is that I will still evaluate, that is W is 1 minus x by L theta W1 plus x by L W2, and theta is 1 minus x by L theta 1 plus x by L theta 2. Both I will use, but I will evaluate bending strain energy as I did it for the this thing, that is EI by 2 d theta dx. So now d theta dx whole square. So now d theta dx will be constant, because this is a linear interpolation. Now, but while shear energy, that is shear strain energy, which is negligible in case of a thin beam. So here what I will use the same expression KSGA. So shear strain energy is dW dx plus theta, so whole square dx, but I will use the same same expression for the strain energy, and I will not use theta is actually dW dx. Now here if you see that this is constant, right? Now this is linear. So this creates the problem. Now while evaluating this strain energy or its contribution to the stiffness matrix, I will do, instead of linear here, I will use constant term, right? So, or essentially I will integrate this quantity with a lesser order of polynomial, but in my bending energy I will fully integrate. So that's the actually technique that is called reduced integration. What numerically it means? Numerically it means you have not learned Gauss quadrature right now, but in the subsequent lectures you will learn what is Gauss quadrature, or if you have an idea of numerical integration, I can just explain it with the midpoint rule. For instance, if you try to evaluate this bending strain energy with a midpoint rule, right? So what is midpoint rule? So midpoint rule is nothing but, if there is a curve, So you want to, so you divide first this curve. So these are my divisions. So these are my, this is x. So this is say delta x. Okay. So now these are my functional function values I know. So what I do with the midpoint rule, I choose the midpoint between two values, that is x1 and x2, for which I know which is my f of x1 and this is my f of x2. So now these two values, instead of just doing it at the this thing, I will just take the midpoint of this form, which is x1 plus x2 by 2, and then what I will do, I will try to evaluate this area. So this is my midpoint rule. So instead of actual area which is bounded by the white curve here, I will compute this is my this approximate area which is a rectangle essentially. If I do that, then it is known as midpoint rule. So now while evaluating this strain energy, so if you see that finally the strain energy or this quantity essentially dw by dx plus theta is essentially a linear polynomial. Now to integrate a linear polynomial, at least you need two-point quadrature rule, which you will learn in later classes. So fully integrate or actually exactly integrate a linear polynomial, you need at least a two-point integration rule. Now to alleviate that, if I use a one-point quadrature rule, then it will be approximated or it is not exactly integrate the linear polynomial. So that's how we reduce the contribution of the strain energy, shear strain energy in the formulation. So for instance, if you see what happens if I just choose the midpoint rule in evaluating this equation, then what will happen is that, so I will write an approximation for this. So if I take KSGA is constant, then KSGA is actually dw by dx and plus theta, which I have to evaluate at x equals to say L by 2, and then also this is my midpoint rule. Now if I just substitute my interpolation for theta and dw by dx, then what I will get is ksga L. Now so there is a half there, so there is a by 2 there, so by 2 into dw dx is we know that is w2 minus w1 by L, and then this one theta is 1 minus x by L, and theta 1 plus x by L theta 2. So this is my, this whole quantity has to be evaluated at x equals to L by 2. So this is if I now do this, so if you will see that this quantity leads to so W2 minus W1 by L, plus if I just substitute L by 2, then it will come as theta 1 plus theta 2 by 2. So now if you see, so this is constant, this is also constant, right? But this doesn't imply that this is actually equals to dw by dx. Okay, so or that means that this is known as the reduced integration. So reduced integration. So what I did here is actually this quantity, if I this is constant for the body, or this is constant for the element, and this was linear earlier. Now by reducing the order of quadrature, I make it constant. so that it is compatible. So this is a numerical technique. This numerical technique is known as the reduced integration. We will learn this thing later in much detail, because this requires a little bit of knowledge of Gaussian quadrature, which generally in finite element analysis we use. Now this is still evaluated with the full integration, that is the so say for instance, let us assume now that is we know 2-point quadrature rule. So this will be evaluated with the 2-point quadrature rule, while this quantity will be evaluated by the 1-point quadrature rule. And in 1-point quadrature rule, that is dw dx will be exactly integrated, but theta, since it's a linear interpolation, it will be reducedly integrated, and so this term will lead to a constant theta, so which is actually inconsistent, but this solves the problem. This is known as the reduced integration of the reduced integration in finite element method. So we'll learn this in detail later. So what I will do now is that I will just write the stiffness matrix, or I will just calculate the stiffness matrix. So this looks like, if you use, so the advantage of this, we use, so our finite element stiffness matrix will be still 4x4 here. Because we won't be having 5x5, which we observed in the earlier case, even though we can reduce it with the elimination of the mid-node displacement variable. So now here we'll use the same that is 1 minus x by L W1 plus x by L W2 and theta as 1 minus x by L theta 1 plus x by L theta 2. Now this element is similar to what we have used for the Euler-Bernoulli beam element. So this is what the same thing. There is no mid node. So now here W1 theta 1, W2 theta 2, and similarly Q1 Q2 and Q3 Q4. So that is your moment and shears. Now here if you look, so we need to recall that stiffness matrix expression to compute the stiffnesses. So if you remember that Ke is having a block matrix, that is your K 1 1, K 1 2, this is just K21 and K22. Now this K12 and K21 are transposed, so we know that. So now since the bilinear form is symmetric, so that's why actually the stiffness matrix will be symmetric. So now K11 is essentially Ij if I do, so that is actually Ks Ga dw instead of dw dx, now I will say d phi I dx and d phi I phi j dx. So this is the same. So now this is the K11 term. Now K12 term Ij is essentially again Ksga is d phi I dx phi j dx. So this is actually K21 ji. So now this is also we know. Now this is K22 ij, it will have two terms. So this is say 0 to L. So now the first term in K22 will be having a bending term. So that is your Ei d phi I dx and d phi j dx, and this is the first term, and then the second term is coming from the shear contribution, that is your gks or ksga phi I phi j. Now this is my stiffness expressions. Now you see here if I want to use the reduced integration, so this term and this term I can fully integrate. Only this term, which is the coming from the shear strain energy in the bending term, that actually this is essentially a bending stiffness. So the shear part of the bending stiffness I will just reduce it. I will use the reduced integration. Now so if I just now do this, so K11 will looks like this, the same, the bar stiffness matrix, but with a Ks Ga. Now this is by L will be there, obviously 1 minus 1 minus 1 1 1. So this is my K11 submatrix. You see this submatrix is 2 cross 2 matrix. Now K12 K12 also we can integrate and we can see what is K 11. So that is KSGA by 2. So it is fully integrated. It has nothing to do with the reduced integration. So now this is actually the minus 1 minus 1 1 1. So this is my K12, and similarly K21 is the transpose of this. So now the main interesting change is here K22. So K22, the first term I will use the usual bending stiffness or the fully integrated. Now you see these are constant terms. So because phi is a linear polynomial, so essentially here what I mean by this interpolation is that is phi 1 W1 plus phi 2 W2. Now here also this is phi 1 theta 1 plus phi 2 theta 2. So both the terms are essentially these are the constant terms. So I will just fully integrate it. So now if I do the fully integration, then this is just a bar stiffness matrix EI by L, but it's a bending term, not the axial. So 1 minus 1 minus 1 1. So this is the bar stiffness matrix. Now the second term, which actually a linear variation, so I have to use now the reduced integration, just because otherwise the theory will be very much inconsistent and the bending term will be 0, or actually it will show the locking. So now the second term what we will have is that we know that is it has to be constant. So and second terms comes out to be KGSA by 4 1 1 1 1. So this is the reduced form. So that's the basic change in the here. Now if you just because these linear term has to means linear variation of phi has to be is suppressed by the one order less quadrature rule. So that means that strain energy corresponding to shear force is reduced actually, and this is consistent with the theory. And this actually, in case of a thin beam, actually this actually very close to the Euler-Bernoulli theory, because dw dx must be equals to theta. Now if I just write the final stiffness matrix, then what will happen? So first let me okay, so this is again a 4 cross 4 matrix will be there, but let me write out the variable first. So that will be W1 theta 1 W2 theta 2. So only change is this, that is the similar to Euler-Bernoulli beam will have this. Now this will have something like F1 0, F2 0, and just like what we did for the Euler-Bernoulli beam, and then we'll have this equation, that is Q1 Q2 Q3 and Q4. So this is it is. Now here so I have to just put these block matrices, which will create the 4 by 4 matrix. So if I just put the block matrices, that is this equation, this block matrix, and this block matrix, and this block matrix. Now remember that K11 is actually corresponding to W1 and W2. So we have to, so this will come in the first row and this will come in the third row. So that, because we have arranged the variables in like that, in that manner. So now if I write this, that is Ks Ga by L, that is my first term, and then the then this theta 1 term will come, which is coming from this here, because this is theta 1. So now minus Ks Ga by 2, right, Ks Ga by 2. So and then again this term, so this is how Ks Ga by L, and then again this term, that is minus Ks Ga by 2. Now again the second thing is theta 1 variable, so this term will come. So again Ei by L, Ei by L will come, because this is thing, and then this term will come. So that is Ksga. So here there will be L in the integration. So Ksga L by 4. So this term will come, and then again this term will come. So half of Ksga by L by 2, and then again this term, that is Ei by L minus plus Ksga by 4, this is into L. So let me write it little bigger. So Ksga, now this is Ksga L. So this is the fourth term. Now here again we'll have this this term, that is Ksga by L, and again I will have this term. So sorry, this term, that is my half of Ksga by 2, and then again I will have this term, that is Ei by L plus Ksga L by 4. So this is what my stiffness matrix looks like, Ksga L by 2. So this is what my stiffness matrix looks like. So this is a 4 by 4 stiffness matrix. Now this 4 by 4 stiffness matrix is very similar to what we derived for the Euler-Bernoulli beam, but this is for Timoshenko beam. So naturally these values are different. So component of the stiffness matrix will be obviously different. So this is the two way. Now if you compare these two thing, you will see that stiffness matrix for the this consistent interpolation and stiffness matrix for the this reduced integration is very much similar. Only difference is essentially the force vector. So the force vector, for instance, if you use a constant force vector, then it is evaluating it very easily, that we have seen earlier. So That's all. So we have learned basically two things. One is essentially a consistent interpolation. Where we can apply different order of polynomial for the interpolation of W as well as theta. And one is reduced integration, for which we have just given you the primary idea what it means and what is essentially the problem. So essentially, when the beam goes to when the beam thickness reduces, your finite element solution locks. So what locking means? So the locking means is that meshes are not enough capable of representing the deformations or representing the solutions. So that locking is not due to a numerical phenomena, rather its origin is from mechanics or the theoretical phenomena or the theoretical assumptions that we considered. So to alleviate that, there are numerical solutions. For instance, reduced integration, one of such solution. But another way of looking at it is a mixed formulation or mixed variational formulation, where we interpolate stresses as well. Instead of deformations, we interpolate stresses. So for that, there is a different variational principle, which probably will not cover here. For instance, Hu-Washiju variational principle, or two-field, that is Hellinger-Resner variational principle, and hybrid kind of formulation, where stresses as well as the displacements are interpolated. So that kind of mixed formulation is also helpful to alleviate the locking in finite element problem. So we'll just stick to the reduced integration phenomena, by which numerical tweaking or considering the numerical rule differently, different numerical rule, we can just compute the finite element stiffness matrix, which essentially considers the here, for instance, the shear strain energy we take actually consistent with the theory in case of a thin beam. So this completes our lecture. So in the next week we will start with the some problems in this area. So let us meet in the next lecture. Thank you.